Hi, welcome to another video in my ongoing quest for unboxing reality, essentially trying to transmit and communicate as many arguments I can find and muster to invite the world towards a change in our conventions and our practices, and all of that with the clear aim to go to the roots of our mistreatment of the world and our waste of energies and materials and our blatant destruction of what we call the natural world, of which we are an integral part. And I find myself within conversations quite often that sometimes are really nice and resonant and inspiring, and at many other times rather frustrating and difficult, which in part has to do with my emotional investment in this, and my deeply felt knowledge or deeply felt belief or insight that what I try to communicate here really does matter and really opens up unbelievable pathways to a different kind of relationship between us and the rest of the world. But very often this is falling on deaf ears, so to say. And today I would like to present another approach, another set of arguments that I went through last night, trying to make a point, which again fell on rather deaf ears. But nevertheless, I think this is interesting. And first of all, let's just quickly put together a short list of let's say characteristica that we like to, or values that we always put on our common sense understanding of the world. So we believe our understanding of the world to be rather efficient, and logical, and that's a very short list. What else? I don't know. You see, I'm still reeling from last night. Never mind that list. Let's just go right into it. So, our conventions that we learn with mathematics, that stem from geometry and originate in the Mesopotamian cultures and Greek cultures, so the Mediterranean cultures in a broader sense of the antiquity. Our mathematics are based on a set of axioms that we take for granted and that we believe in to be true, and yeah, I think they are rather dogmatic, and they are also biased, incredibly biased, and really not helpful in a lot of sense to our situatedness in the context of this cosmos and this world. So what I'm trying to get at is, let's for the moment use our conventional way to define an area. So when we do that, we usually speak of the part of an area that is inside of some lines that we draw, and we usually don't care for what is around that area, which is part of the conventions and the troubles. Because really, when I put any kind of polygon on this paper, and the paper is important because it holds our polygon, when I do that, I do not only inscribe the inside of my polygon, but also I define the outside. But that is already far off because this is synergetics and we're not yet there. So I want to, and I'm using metric system here because I'm living in Germany and this is what we use. So what I want to define is an area of 100 square centimeters. So what I need for that is a line that is 10 centimeters. We have that here. And now, if I do not use and apply a broader sense of more complicated tools like this, which this would make it easy to draw squares and right angles by its very nature. But if I stick with the old school, with ruler and compass, there is a bunch of possible constructions that I can use to create a square. But I'm gonna use one, and let me just set up the compass here. So imagine we are in the very beginning of geometry, when there was no fancy schmancy tools of any type. You would be stuck with the simplest tools that you get. So I draw what I need first is a perpendicular to that line that I drew. So I'm creating two arcs from my two points here that define the line that we want to extend to get our area. Right, so what I'm doing is I draw this, and just to note that quickly, what we have created now is already a vesica Pisces, as it is known, which, if we were to connect all these points here, would unveil that we drew two equilateral triangles, or what I call leftangles. So this is the first step of construction, and it already points to what I'm trying to argue for. But let's not get into that right now. Instead, we want to build up on this. So now we need the perpendicular, So here's our first line that we draw as an 8 to create this thing. And now what we do is we go into this point that we just got and take a new radius from here to our first point there, and we draw oh, that is not exact. Surprise! How about here? Yeah, more or less. This doesn't need to be all exact, but close. Okay, so now we have drawn another semicircle, and you see I had to change the setup of my compass. So to recap, we already drew 2 triangles and an additional line for reference, and we had to change the setup of our compass. And now what we gain is this point here, which is incidentally the center point of our square that we try to draw. So with that I can draw 2 diagonals for the square, and you see how it goes there and meets that circle that we drew earlier with the radius of 10 centimeters. And we go this way and we meet there, and those are the other corners of our fancy square. So if I'm going to take that. If I now go ahead and connect those lines, magically and surprisingly we gain our square. Alright, so you see we had to draw 1, 2 circle arcs, 3 with the third one with a different setup. Then we had to draw 1 additional line and 2 more that are the diagonals of our square, which are incredibly important for the square, but that's the part of the story that I've been telling in different kinds of videos. So now this is interesting because we have just created or defined an area of 10 by 10 centimeters, which means the area of this is a to the power of 2, which is 10 to the power of 2, which is 100 square centimeters. Awesome. But how about the circumference of that? That should be 4 times the 10, right? So the circumference is 4 times 10 centimeters, which is 40 centimeters. Surprise. Okay, so far so good. This has been all conventional and easy and peasy and oh so efficient and logical, right? Except has it been? I'm not sure. Because now, if I wanted to do something else, if I wanted to have an efficient use of the area here, one that has a better relation between the area and the circumference and thus the surrounding area, and less complication in the construction, I can turn to away from the right angles towards the left angles, because remember we already had this here. There is our left angles already in our construction. And my point is that, or my point and the point of synergetics is effectively that rather than having that framework, we could use this and make that our logical framework. But first of all, if I wanted to have a hexagon with the same area, so here is a sketch of a hexagon, more or less, and that is supposed to have an area of 100, what we call square centimeters. How long has the edges? How long is the edges? And the edges and the radii of our hexagon are identical, so there's a bonus. To get the hexagon's edge, we need a formula that I have on my cheat sheet. So the area of a hexagon is 3 times the root of 3 divided by 2 times the length of our edge there to the power of 2. Okay, that is not really simple, is it? It seems rather complicated. But now we know the area, that's 100 square centimeters, so we have to change the thing to get to our length, to our edge length, and that would mean setting that around and about. We say our edge is the square root of 2 times the area, 100 square centimeters, divided by 3 times square root of 3. Okay, that is a rather complex calculation, but I fed it into my calculator, and the calculator told me this is about, and that is really about, it's not, you will never get a perfect solution from this, because there's already a whole lot of irrational stuff in there going on. But this is round about 6.204 centimeters. Aha! So what we get here is the 1 unit of measurement we need to construct and create our hexagon. So let's switch from right angle to left angle. Take this, and now let's pick our 6.2. Let's start like we did before. We would start with a line, and this line is gonna be 6.2, like so. This is the A of our hexagon, right? So now we go to that point here and make that the center of the hexagon, and we take that radius 6.2 about there, and we draw a full circle. Whoa. Okay, anyone who ever played with the sacred geometries is familiar with this. Next step, this is the so-called Vesica Pisces, and it was incidentally the first thing we did on the other construction as well. So now we got essentially 2 left angle triangles. This would already be enough to construct the rest of the hexagon. I could just take my ruler and go from these points that I just got here through the center point to the opposite side and already get all other points that we need. Possibility 1, and the other one, which is maybe a little bit more beautiful, is to just continue with this. You see, so here we go, and we do not change anything about the setup of our our compass, and we do not need any kinds of beautiful additional lines. All we need really is that. And now, almost magically, we've just gained our hexagon. Oops. There you go. But, and this is a big but, a big crucial but, this hexagon really, if you complete it, contains 6 triangles, 6 equilateral triangles, or what I call left angles. So this is our edge that we began with, which is 6.2 centimeters, and that is true for all the other lines here. Both the radii and the circumference vectors are 6.2 centimeters. Only one measure, right? And now the area of this thing, as we have calculated before, is, on the inside of that hexagon, the area is let's just do that again for fun, or no, maybe not. No, we don't need to. The area of this is 100 square centimeters. So it's the same area that we drew first with our square. But there's a difference, because the circumference of our square here was 4 times 10 centimeters, and now we have a circumference that is 6 times 6.2. So circumference is 6 times 6.2, and that equals 37.2 centimeters. Okay, so what do we notice here? We have the same area, but we have not 40 centimeters. 40 centimeters as we had here, but we have 37.2, and 40 minus 37.2 is 2.8. 2.8 centimeters difference. So our square has another 2.8 centimeters of circumference compared to the hexagon. Now, that doesn't seem much, but it makes quite a difference, because this is true in any case. If you want to put your garden out and you want to place as many beds in there as you could, or you want to arrange anything, anywhere, and you want to make it efficiently and with the least amount of waste, material and space and all that, the logical choice is not the square, but it is the hexagon, which is much less complicated to construct, and it is much more efficient in its use of inside and outside, because yes, it has what it really means if you have a lot of area with a little circumference is that you get a lot inside without taking much from the outside. That is important. And another thing is, we notice that a part of the complicated calculations that we have gotten, because our unit, our reference unit is that square, which is already a complex system, we have created this hexagon from 6 of these triangles. So if my point is, if we go with synergetics, we redefine our unit for area to be a triangle instead of a hexagon, and that is only reasonable for a lot of reasons, because what we do when we take the second power, what we call squaring, where we essentially make bigger squares from tinier squares, that comes from the triangles. You see, if I have a triangle here and I get the midpoints of the edges and I connect them, I get 2 times 2 is 1, 2, 3, 4 triangles. So that is the square of that 2 edges. And this holds true if I increase the frequency of that, like so. Now we have 3 times 3 is 5, 6, 7, 8, 9. Right? So our tool of area calculation is just as easily feasible with triangles as we are used to with the squares. Even easier, I would say, because to get here we already have that. And to define a plane, which is what the area thing is all about, we have to have 3 points. Sorry, I had to get my cat inside. 3 points make a plane, 4 points don't. Here I am out of frame. Yes, and why am I going out of frame? Because I wanted to get these. Because we have been drawing on paper, and the paper is a body itself, has a structure itself, and was able to hold our lines in place. If I were to draw that, to try to make that square without the support of the triangulated paper underneath, I would run into this problem. There is no structure in the square, and there is no diagonals which can actually hold this, whereas the same material, the same connections in a triangle actually hold a shape. They define a plane, and it is only logical, if you want to measure and account for area, to take the most simple unit for that and not a complex one. So with this as my unit, if you see, if I go back to this hexagon here, now I got 6.2 centimeters here. So how many triangle centimeters would that be? That would be 6.2 to the power of 2. The same thing that you do with the squaring. I don't know that out of my head right now. 6 to the power of 2 would be 6 times 6. That should be not 30 but 36. Yeah, 3 dozen, of course. So if we just, for making this a little easier right now, don't mind the 0.2, then this would be 36 triangle centimeters. And by knowing that, we can also say that the whole hexagon has 6 times that area in triangles. And so the accounting for the area of the hexagon, that becomes really simple and easy to do when we have a unit of area that is a triangle and not a square. And this is only in what we are used to think of 2D, which is an abstraction, because of course the paper and even the lines that I draw on have a third dimension to them. They are embodied time space, so we are talking about planes here, but this is also true for space and for volume. So using that unit, the triangle, the left angle as unit, also for volume, we get to the tetra and the octa and many other shapes that are completely irrational when we use square and cubic accounting, because everything that is not square or cube becomes irrational immediately, whereas it's nice and rational and simple and easy to do when our unit of reference is the triangle and not the square. So I hope this little rant was interesting and possibly helpful. And let me know what you make of it, and if this makes any sense to you, and if you want to learn more about this and get more into this, then please don't hesitate to ask me, or check out all the videos that I've been doing, where I so far have been more into the practical and spatial extensions of this, and haven't yet focused on this kind of dry geometric mathematics. But even in those, even there, we can see that those attributes that we put to this convention that say it's efficient and it's logical and so many more useful and whatever, those do not hold true. It is not efficient to draw this, as I need much more complicated operations to get this than to get this. It is not logical to use this highly complex kind of shape as a unit for something that is incredibly uncomplicated in its origins. And that is only the beginnings, if you go into the effects of this thinking and this sense making that we force onto the world, onto ourselves, and both humans and non-humans alike, then the effects are catastrophic in a global sense and also in local senses. this is why we need, this is at the heart of patriarchy, of civilization, of oppression and warfare and extraction and colonization and all these things. So if we really want to decolonize ourselves, our thinking, our acting, our relationship with our greater selves, which is the planet and all its inhabitants and ultimately the entire universe, if we do want to decolonize those relationships, I am absolutely sure that we cannot help but get rid of this invalid and illogical and inefficient and wasteful and violent framework, and instead turn to something that is logical, efficient, beautiful, simple, easy, and universally applicable to all kinds of things, all kinds of things. So, with that, I hope you didn't fall asleep. If you want to try some of these constructions, check out this book. It's really nice. If you want to know how to make these, check out my videos. And just to see that this is also an important point I can't stress enough. When we think of geometries, we tend to think of these kind of ideal, perfect, uniform shapes where everything is straight and exact and stuff, but it doesn't have to be that way, because my table here rests on that, and you can see this was a piece of oak that I split in 12 parts, and then I did take away the sharp corners a bit, and what I did was connect the corners of this with wire, so there is a hole through the wood and the wire goes through and around and through again, and so I can make a knot here in this corner, a connection that does not have to be rigid. It doesn't have to be, because the shape itself is what gives structure and stability. And this thing is stable. Yes, it can move a little from here to there, but it is stable. And I cannot stress enough that this works not. This couldn't work if I tried to use the same material and connections to make a cube. It just couldn't. You need a lot of extra effort to make a cube that holds shape. And our accounting, our thinking, our sense making, that is always working with the idea of a square that is non-triangulated and a cube that is non-triangulated, that makes it really hard to get rid of all the approximations that we have to do and get to the core, to the bottom of what makes our reality work. And I don't want to make that sound like it's a mechanical thing or anything. I rather think it's like the Taoists say, nature is by itself so, because nature is just following the path of least resistance, of least effort, of incredible beauty, and that is a path that is open to all life, and it is the path that most life is following, even us, except in that point where we start abstracting ourselves away from this world and force upon the world a framework that is inherently wrong. It's a mistake. Yeah, that's it. I hope you have a good day. Bye bye.